All right, cool. So I'm going to go ahead and get started. Thank you all for coming to my session about using a Kubernetes operator to manage tenancy in a B2B SaaS app. So on the internet, most people call me Arpaia, except if you're on Twitter, because Arpaia was already taken. I'm Mike Arpaia. That's relevant because there's a bunch of code snippets in my deck that you probably won't be able to read, although this screen is really large, so maybe you will be able to read them. But I tweeted out my deck earlier. It's also on the sketch for my talk, so don't worry about taking photos or anything. You can find all of that on the internet. So a little bit about me. I'm the co-founder and CTO of an infrastructure analytics startup called Kolide. I used to work at Facebook, Etsy, ISEC Partners, a few other security companies doing security infrastructure stuff. I was also on the Kubernetes release team for 1.11, 1.12, and 1.13, doing release notes stuff. And that was awesome. Love the release team. I also was the creator of an open source tool called OS Query when I worked at Facebook. Some of you may be into operating system monitoring, may be familiar with OS Query. I love Go. I'm an enthusiastic Go developer, as I like to say. I've been writing Go since Go 1, and I'm all about it. And I play the bass, and I love skiing and climbing and hiking and trail running and all that good stuff. So that's all you need to know about me, really. About Kolide. Kolide is an infrastructure analytics company. B2B, we basically sell, we have a web application that does operating system analytics for our customers. The principal thing that you need to know about Kolide for this presentation is that we have a SaaS product. We sell it to other businesses, and the data that we collect from our customers is the most sensitive data that they have. So security is super important to us, and that motivates a lot of the decisions that we make around data isolation and architecture. So keep that in mind. I also want to give a shout out to the two SREs that work at Kolide. On the left there is Victor, and you may know him as Groob on the internet. And on the right is Seth with an S, not a C. And you may know him on the internet as Directionless. And they have been super instrumental in this whole process of both coming up with all of these ideas with me as well as putting them into production. So couldn't have done any of this without those two guys. So for the talk today, I want to discuss a few key concepts in the multi-tenancy space and make sure that we all agree on some shared definitions. I want to give you a quick rundown of how we chose to deploy our application and manage tenancy at Kolide. And then I want to dive deep into the Kubernetes operator ecosystem and how we've used the operator to accomplish various aspects of operating a production system, such as deploying that system, the networking involved, security aspects of it, what have you. And then I have a few links to various community projects that hopefully you may be interested in, as well as some enumerations of lessons learned, interesting gotchas, and other things that you might want to take away from this presentation about whether or not you should or should not do this based on the different properties of your business. So let's hop right into it. Some multi-tenancy concepts. So this talk's all about application tenancy, and that is the companies that create products for other companies have to reason about the isolation between the different companies. And there are two complete ends of the spectrum on how you could go about managing application tenancy. One is to create a kind of monolithic application which handles tenanted data isolation via application logic, middleware, stuff like that. And the other end of the spectrum is to deploy and proxy to many independent, isolated, single-tenant applications. And this talk kind of, it's choose your own adventure. We chose the second path, and we chose to manage that with Kubernetes Operator, and that's what I'm going to explain. So I just want to explain the spectrum and that you may or may not choose that path, but if you do and you want to manage it with Kubernetes Operator, this talk's for you. And I'll talk about at the end, I'll talk about some of the properties that it may be a better idea for you to consider one way or the other if your organization has different kinds of properties. So within the Kubernetes space, people often talk about hard and soft multi-tenancy as the terms, and I think it's useful to understand these two terms. Jesse Frizzell it has a ton of interesting documents that she's written. She used to be the lead of the multi-tenancy working group and wrote a ton of really interesting documents on this topic. And I like her definitions of these two topics, so I'll read them to you. Kubernetes is the new kernel. We can refer to it as a cluster kernel versus the typical operating system kernel. This means a lot of great things for users trying to deploy applications. It also leads to a lot of the same challenges we've already faced with operating system kernels, one of which being privilege isolation. In Kubernetes, we refer to this as multi-tenancy, or the dream of being able to isolate tenants of a cluster. So hard multi-tenancy is really this idea of you want to, a common use case for hard multi-tenancy might be if you're selling Kubernetes, like if you're a Kubernetes provider and you want to give someone a control plane that only they have access to. But you perhaps want to run all of these like Kubernetes clusters that you're distributing in Kubernetes. This would be hard multi-tenancy. There's no shared infrastructure between the tenants. The other is soft multi-tenancy. Now, what Jesse wrote about soft multi-tenancy is multiple users within the same organization in the same cluster. Soft multi-tenancy could have possible bad actors, such as people leaving the company, but users are not thought to be actively malicious since they are within the same organization, but potential for accidents or evil-leaving employees. A large focus of soft multi-tenancy is to prevent accidents. I think that last point is really important. So the common use case for soft multi-tenancy is if you're a cluster operator at a company and there's a lot of different teams that each want space on your Kubernetes cluster. This is soft multi-tenancy where you can kind of trust people, but you want to put some guardrails up. So when we think about hard versus soft multi-tenancy, it's a big spectrum, and there's a few key points of isolation that you can trigger, and then everything in between those points is kind of a little more ethereal. But the SaaS application multi-tenancy problem space is firmly soft multi-tenancy. So we're not really interested in super concrete isolation between the different tenants because we're a set of operators that wrote all the software that we're deploying, right? So we trust the software. We trust that, it's not like we don't even have to deal with employees being disgruntled and trying to, circumvent our protections because we're not giving our employees unfettered access to deploy whatever they want in our cluster. So multi-tenancy for us is more of this logical operation, and that's something to keep in mind. Another topic that's often talked about in multi-tenancy that I'm not going to talk about at all today is metering. And this is really popular in CoreOS's operator framework, and this is the idea of controlling how many resources a single tenant can use compared to another. We don't do any metering because that would imply that we want to kind of limit the computational resources that one of our own customers can use via our own software, which wouldn't really make sense for our use case. So we don't do any metering, but there's a lot of really interesting metering stuff out there if that's interesting to you. So keep that in mind. All right, cool. App architecture. So I want to talk to you a little bit about the chosen architecture that we have for this, that I'll go over for this talk, because I think it's useful to understand the kind of general goal of the deployment model, and then we'll go into how we accomplish that. So generally, single application instance per customer. So there's various components to the application. This is a contrived example where there's just 3 components. One on the top left, one on the top right, one on the bottom. And all of the boxes represent various infrastructure components, but the key here is that each compute and data requirement of a tenant is completely isolated into its own box. And there are a few advantages to this, a few disadvantages to this. This optimizes data and compute for very sensitive use cases. Like I talked about, we do operating system instrumentation and analytics for security reasons for our customers. So this is very sensitive data, so we don't want any risk of cross-pollination of that data. And this also eliminates the need for product developers to reason about data isolation and multi-tenancy, which are historically kind of complicated topics. And if you find yourself at an organization that has a lot of infrastructure folks but not a lot of product developers, this might be a compromise that you can make to offload your product developers from having to reason about multi-tenancy if you can make it an infrastructure problem. And also, we're a startup. We did our Series A like a year and a half ago, so we're pretty early stage still. And this allows us to have our infrastructure orchestration and account management, deployment tooling, all of that kind of outlast any products that we want to try out and spike. If someone wants to write a new version of the app and deploy it to a few tenants, we can do that because it's all rather decoupled. So, a few interesting considerations. So once you have these little clusters of applications, the general strategy we have is that we deploy all of them independently, and then we have a networking layer that exposes a single unified ingress, and that ingress takes care of routing traffic to customers based on some per request identifiers. And I can go more into what those are later. There's like a networking section, so we'll get into that. But that's the goal. We've got these little boxes. These boxes are full of application components. Each tenant gets their own application components. We ingress at a unified point and then route to all of them independently. And note that, we'll get to this, but this doesn't always, it's not always in one cluster, right? We reached the limit of what we could handle with one cluster and had to reason about doing this kind of multi-tenant ingress for many clusters. So that's its own interesting consideration. So this talk is really about managing tenants with an operator. So once we decided on this architecture, it was pretty, and we've been using Kubernetes for a while, it was pretty, pretty obvious path that we should go down. So each tenant gets its own Kubernetes namespace, and all the compute resources live there. We also have a higher level control plane for things like sign up, routing, that Ingress proxy that I talked to you before, account management, deployment servers, stuff like that. So let's take a quick aside and talk about the operator ecosystem for those of you who either are not super familiar with operators or not super familiar with the software development ecosystem around it. So Kubernetes operators are operator is this kind of marketing term that CoreOS made up a few years ago. I like to define it concretely as a combination of a custom resource definition and a controller. And your custom resource definition represents the schema of your, well, I'll get to the definition of each of them. Kubernetes operators are awesome. So yeah, so for this talk, I'm not really going to use the term operator anymore. I'll use CRD and CR to reference the custom resource definitions and the custom resources, and I'll use the term controller to represent the deployed thing in the cluster that interacts with the API server and takes action based on the instances of the custom resource. All right, awesome. So CRDs are really awesome. The CRD API is kind of a popular topic at the conference this year, which is great. And I love it because the source of truth is an annotated Go struct, which works directly with all of the Kubernetes API machinery. And when the source of truth is a Go struct, that always makes for a great day in Mike land, so that's awesome. And it's a neat standard to adhere to since, everyone kind of has the YAML problem. You've got too much YAML, you don't know what to do with it, but at least, if somebody figures out a better way to manage all the YAML, everyone can use it. So I don't have a great YAML solution for you yet, but when one comes out, I'm sure we'll all benefit from it. Now, the difference between custom resource definition and a custom resource is also one of interesting note. So custom resource definitions are like the schema, the specification, what fields you're allowed to set on this object. And a custom resource is, it's just a resource. It's one instance of the custom resource definition. And I think it's worth being explicit about using CRD and CR appropriately when when you're talking about the different things, whether you're talking about the schema of the resources or a specific resource. So this is great because we call our custom resource definition tenant, and you can get all of your custom resources by doing things like kubectl get tenants and stuff like that. So sometimes, like I said, it's parameterized via things like Helm and Ksonnet, and I use Helm because I don't like the tiller, but your mileage may vary. So this is kind of, this is, I think, the only place actually in the talk where the custom resource is shown, but this is a, just a rough example of the kinds of things we have in here for each tenant. So for, we have the name of the tenant, which are just these like random strings. We have a few databases, so if you want like 2 MySQL databases and a Postgres database for one tenant, you can enumerate those there. There's some high-level aspects of the like account management bits. So when a user signs up, we create the tenant, we include these account management bits so that we can invite them or send them an email saying their instance is up and running when it's ready. So, it's useful to have all that information there. And then we have some random information like how large the PG Bouncer pool size should be. And, these are things that we've just kind of iterated on. And then the main bit, the repos bit, is all of the different microservices that make up our tenant. So, there's only 2 listed here, but in practice, there's several more on each of our tenants. So, that's in there. And then, we basically specify the container that gets deployed and then some parameterized YAML, which we have like kind of a Helm-esque templating engine that we use that's like Helm except without the tiller. So controllers are the other side of custom resource, or the operator pattern, right? Controllers are long-running, single-instance processes, typically written in Go, that interact with the Kubernetes API server to observe how your custom resources are changing over time, and observing what the state of the custom resources is, observing the state of reality, translating the domain-specific information about what needs to happen, and taking action on your cluster based on all of its observations. So there's a lot of different ways to write controllers in Go. I based this operator off of the sample controller, the github.com/Kubernetes/sample controller, which is produced by the API machinery. And it's a little more, we wrote this before the operator framework was around. If I could go back and do it, and if the operator framework was around when we started the project, probably would have used it, but I don't regret not using it because now that we've used sample controller, we just have a lot more control. So I would say if you're not afraid of dealing with the Kubernetes APIs very deeply, then go for the metal. Try to get as close to the API machinery as possible. But if you're new to Kubernetes, but you like writing Go, the operator framework is definitely more user-friendly API. But I encourage you to get familiar with the Kubernetes APIs in Go if you're a Go developer, because once you learn the general patterns, they're all very consistent, and it's really easy to work with. So, go for it. So I'm going to show you a few code examples of our controller, just to show you how we do just to show you the general life cycle of, controller starts up, how do we do initialization, and how do we get into this control loop where tenants are managed. So, and like I said, you're probably not going to be able to read most of this from your seats. That's fine. I just want to exhibit, the smaller the text is, the more it's kind of on purpose, because, the more kind of unfortunate initialization you have to do. So this is the main, so when you're starting up, when you're creating all of your Kubernetes API clients and stuff, you have to get all your kube configs, and you have to create all of your informer factories, and your factory factories, and your factory factories. And then at the end of the day, you can start a run loop, and that's at the bottom. You see c.run, and you're running your controller. So basically initialize all your Kubernetes API dependencies, your Kubernetes API clients for all of the core types, as well as all of the types that your custom resource definition is adding. Once we get into the initialization of the controller itself, when we initialize new controller, it accepts to all of those initialized bits from main, and then further initializes informers. And what informers are these kind of event-based API objects that you can instantiate that allow you to watch. You can watch objects as well as have an in-memory cache of objects that the API server knows about, so that you don't have to hit the API server every time you want to list the namespaces in your cluster or something like that. So for a very, very slight memory hit, you can have all of this stuff cached locally, which is really great. So if you're listing out deployments or secrets or namespaces or pod disruption budgets or any of the other stuff that you invariably will need to operate on, creating all these informers is really nice. So you can see there's like namespace, secret deployment, stateful set, services, pod disruption budgets, and then towards the bottom there, there's the tenant informer. So that's our kind of API object for the tenant. And it's great because all of the informer factories and all of that get auto-generated by the code that is part of the upstream API machinery. So there's really great code generation for that. Now, this is where we set up the event handler. So this is kind of an important bit of code here in NewController. And you'll see this is all the way at the end, right before we return the controller struct that we've just instantiated and packed full of informer factories and all that good stuff. We set an event handler so that when a tenant is created or updated, we enqueue it. We add it to the queue. And now the queuing logic is separate, and we'll get to that, but this is just to exhibit that there is a function. There is a function on the controller struct called enqueueTenant, which will add the tenant to the work queue, which is internally managed. Now, synchronization, this is where the magic happens, right? If this was MTB Cribs, it would be the bedroom. But so there's this function we have called resolve tenant state, and this basically accepts a key, and this key is the name of the tenant. So then we use the tenant informer factory to get the full typed struct for that tenant key, and based on the state of the tenant, which I'll explain, we then resolve it in a certain way. So when we first created this, we would just resolve tenants in one way. But then we started to get a lot of customers. Some customers churn out, and you don't want to keep their tenant around, or you want to keep it in kind of this idle state. So we added a bunch of states to tenants. So that's another thing we added to our custom resource definition. And we have different kind of synchronization loops for each one. So I'm not going to go into each of the different resolutions for each of the different states, but you can see the states there are frozen, archived, purged, and then we have a general, catch-all for things like whether they're idle or new or anything like that. We're just going to make sure that they're fully deployed and healthy. So, this is the general life cycle. We instantiate our Kubernetes API clients. We create our informers. We instantiate a controller. We have our little run loop that's provided by the API machinery. And then, based on the state of the tenant, we'll take some different actions to ensure that the tenant is deployed properly, right? So that's all well and good. Now I want to go through the aspects of production system part, where we talk about deployments, networking, security, stuff like that. So deployments. So to facilitate frequent deployments, we, like everyone else, like to deploy as quickly as possible, because it's 2018, and who doesn't like to deploy several times a day? So we wrote a Slack bot that interacts with the Kubernetes API that allows you to, make certain changes to tenants. So let me show you a little example of what that looks like. So we have a deploy channel in Slack, and we wrote the Slack bot called CloudCuddle. So you'll do CloudCuddle deploy, application name, hash. And in this example, the application name is called herd, and Victor is deploying a specific hash. And now what that'll do is it'll talk to the Kubernetes API, list the relevant tenants that you're trying to deploy. Now you could do like CloudCuddle deploy herd that hash -- tenants to Babe, and that'll only deploy that hash for that part of the application to that tenant. If you leave it off, it deploys it to everyone. So the Slack bot here is kind of interacting with all of the different Kubernetes API servers for all the different clusters where tenants may exist, and basically doing like a poor man's apply, which is interesting. I'll talk more about server-side apply and kind of updating and the perils therein. But that's really fun. That's cool. So this is kind of, again, this is something that you can look at in the slides for reference later if you want to. But this is basically going through all of the different Kubernetes clusters we have, resolving whatever tenants were supplied, and going and doing an update. again, this is kind of just going through and in this specific example here, you see the kind of halfway through, we do like a get, we do a list of the tenants, then we enumerate through those tenants, do the update to them based on whatever hash you were trying to deploy, and then do an update operation with the Kubernetes API so that now the tenant is changed and it will be enqueued in the controller. So that's kind of the flow. You write a Slack command, the Slack bot interacts with the Kubernetes API, updates the tenant custom resources. The controller has an informer factory. It observes that these updates have happened and takes the action to converge actual state with desired state. So that's deploys, that's it. Yes? The question is there a reason why we do this in Go instead of just using kubectl and kubectl applying it? Yeah, we don't actually keep any of the tenant YAMLs. Yeah, they're all just, we operate we don't have like a repository of YAMLs or anything. We just reason about them as API objects. Yeah. Networking, new topic. So the most interesting thing that we do with networking is this ingress bit. So for any kind of tenanted sharding scenario, you need a central index for managing external ingress traffic, and there are a ton of options for this. Envoy, you can script with Nginx. There's a really great talk from Shopify at SRECon about this. For our needs, we like writing everything in Go. We wrote a little custom ingress proxy in Go that does exactly what we need and nothing that we don't. We like our custom proxy, although we may reevaluate that as different options become more mature. So a few details about this. This proxy, it's all L4. So it makes it super easy. We just terminate. We L4 directly to the pods for each tenant. So each application is a Go service that is totally willing and ready, willing, and able to terminate L4. So that makes things a lot easier. It's called Shuffler. It's similar to Envoy with regards to the fact that it separates the control plane from the data plane. So we have a gRPC API where we can set mappings, where we can say, hey, a new tenant signed up. We deployed them in this cluster. So create a mapping so that when you see traffic for this tenant name, it needs to go to this Kubernetes namespace. So we use GCP Data Store to persist that. GCP Data Store effectively scales forever for this use case, so it's really great. And then the data plane just kind of gets that, keeps an in-memory cache of that information, and just on the fly makes a decision about where this request needs to go based on the tenant ID that's in an HTTP header. And this adds about 1 millisecond of latency, which isn't awesome, but is definitely not our bottleneck. So we don't really worry too much about that. Intra-namespace traffic within the namespace is interesting. So for per tenant service traffic, we just use the, you can use just, for example, herd is one thing that is in each tenant. You can just refer to it via the DNS herd. This is actually pretty convenient because it allows you to communicate intra-tenant services without having to do any fancy service routing, because every tenant that needs to talk to its herd or its KStore or whatever, it's like service that it needs to talk to for a tenant. It can talk to it via the same name, and you can use network policies, which are part of core, to lock down this network graph, depending on your use case, and we do for ours. So that's an interesting little tidbit. Now, security. Now, this is an interesting one for sure. This is this is interesting from a few perspectives. One of the things that I think is the most interesting, and the thing that kind of not caused us the most pain, but that we spent a lot of time kind of reasoning about and discussing and optimizing, is secret distribution. So each tenant needs a variety of secrets, API keys for things like SendGrid or what have you, as well as the database credentials for the per tenant data resources that it has and what have you. And if you've used Kubernetes before, you likely know that Kubernetes secrets cannot be shared across namespaces. So for the things like the shared API keys, SendGrid, stuff like that, we We can't have like that secret in one place and have it shared by all tenants. We have to manage the distribution of these secrets to every tenant, which is interesting. So the way we do this is we have tooling in the run loop, in the synchronization loop, in the controller, that when we go to deploy a tenant, it will enumerate the secrets that are in that namespace via the shared informer that we have for Kubernetes secrets, observe what's there, observe what should be there, and make any changes necessary. Right? So this. Since we deploy in multiple clusters, we can't use like a single shared namespace or anything as a source of truth. So we have to have some exo cluster secret storage mechanism where we can pull all of these secrets from. So for our use case, we have this little interface that we made called store, which just is get, list, put, delete, and it actually operates on the core v1 secret objects, which is really nice. We use Kubernetes for everything. There's already a typed object for secrets. So we have this very minimal interface for accessing secrets from an external source. And this is what the controller uses to get secrets from that source. Now, for the actual implementation of this interface, we use KMS and GCS, which are GCP products. Basically, we don't use Vault because auto unseal isn't free. So we're already really heavy users of GCP. So KMS is basically a way for you to encrypt very small data. It's just an API. It has like an encrypt and a decrypt RPC that you can call, and then we store the encrypted secrets in GCS. So whenever we need to get a secret, that will go get the encrypted object from GCS, decrypt it with KMS, and then we operate in code with the core v1 secret, even though at rest they're encrypted via keys that we can rotate and manage permissions to with IAM. KMS is a pretty cool product. It's got some gripes with it though. We can talk about that after if you want, if you're into it. Synchronization loop performance is really interesting when it comes to secrets because in your happy path, your synchronization loop happens really quickly. Like if you're just maybe updating the size of the PG bouncer configuration or what have you, making these very minute changes, you don't want the run loop for that tenant to take very long. Right, so another reason why is when you start up a controller, the first thing it does is it enumerates all of the custom resources that it needs to operate on, and it runs the synchronization loop on all of them. So you want your controller to be able to reboot pretty quickly when you have new updates. So you want this, so if nothing's changed, you want it to be able to just work through all of the all of the items that it has to process as quickly as possible. And this process for us was almost completely a practice of seeing how efficiently we could manage the secure distribution of secrets. So a lot of interesting optimizations here, but generally this, we really had to optimize out making any calls to the Kubernetes API server in the hot path of synchronization. So originally when we started doing this, every time we synchronized a tenant, we would list all of the secrets that were encrypted in GCS. We would make a get for each item in a folder in GCS. We would make an API call to KMS to decrypt it. We would list all the secrets in the namespace. We would compare all of them, and then make the changes we had. So we made 40 RPC calls to Google products, 40 RPC calls to the Kubernetes API for every tenant. It was super slow. It took several seconds to synchronize one tenant if nothing had changed. And at the end of all of the optimizations that we made, we would basically pre-stage the shared secrets into a Kubernetes namespace and used shared informers to list that namespace. We would use a shared informer to in-memory list the tenant namespace, compare all those, and then we would only use the GCS storage for per tenant specific secrets. And that basically made this run loop performance a non-issue. So be warned, that was a big deal, and it was a pretty easy fix, but it's something that you have to pay attention to for sure when you're interacting with Kubernetes API in something that could be running highly concurrently, as these work queues often can. So, all right, I'm going to skip that. stuff we've learned. Yeah, so like I said, with regards to performance, it was very much a practice of optimizing the speed at which the controller could work through one tenant when minimal things had changed. When we reached about 1,000 tenants, the cluster started falling apart miraculously in a number of different ways. So we kind of pointed at that and said, all right, that's the max number of tenants we're going to deploy in a cluster. And we started scaling to more clusters. So keep in mind this number may be different for you, but that's where it was for us. We knew that we were going to have a one cluster max. I'll answer your question at the end because I just don't really have much time right now. Another interesting thing we learned, optimizing for customer time to value. When people sign up for your product, they want to start getting value as quickly as possible, obviously. So in order to facilitate that, we added a new state of tenants, which were unallocated tenants. So we would have kind of a worker keeping a pool of like 10 or 20 unallocated tenants, and then when someone signed up, we would just allocate that tenant and drop them instantly into it so that they didn't have to wait for getting an email and having to go back into the application so that they could convert. They would just sign up and immediately be dropped into a user experience. So that's possible to do, and as any product person will tell you, this was super important. We did it really early, and I encourage you to as well if you go down this path. Another thing we learned is health checking. So initially when we were doing this, we would go through we would synchronize a tenant and make all of we would create a deployment, we would create a service, we would create all the API resources by interacting with the Kubernetes API, and then we would just be like, okay, we're done, and move on to the next one. That wound up overloading the Kubernetes API because we would basically go through all of the tenants, make all of these operations, and then all of these things would be pending, and the Kubernetes API server would be trying to interact with all of the different kubelets, and it was a pain. So what we did was at the end of the synchronization loop, we health check the tenant and wait and block until everything is deployed as we want it to, so that the parallelization of the control loop that we're operating on influences how many concurrent tenants we're operating on, so that we don't get to a point where we're, where every single namespace has something going on in it. So, we can adjust the parallelism of the work queue, and that is the total number of tenants that will ever be operated on at one time. That's interesting. So just to sum things up, situations where this architecture works really well is if you have a relatively small number of relatively large customers that have relatively unique resource requirements, where you can really take advantage of your ability to fine-tune each different tenant. That's really awesome. If you have application components written in several different languages, this is really nice because you can kind of piece them all together, and the tenant abstraction allows you to do that really easily. That's awesome. Situations where this architecture doesn't really work out that well is if you have a very large number of very small tenants, because the thing that you're going to optimize is the minimal cost. Like, you're going to be able to compact a single instance of your application as small as possible, and that's great because it gives you a single point where you can be like, okay, well, we know one tenant costs us $1 a month to run, so we need to make that 30 cents, and then we'll be mega profitable. But if you have just a ton of customers that are so small that you need to just run so many of these tenants, then the economics of that probably just won't really work out for you. If your data security requirements aren't very stringent, the juice might not be worth the squeeze. This is very much a data isolation security effort. So if you don't really care about that, this might not be a great move for you. And if you don't like writing Go, you probably won't like interacting with the Kubernetes API. So keep that in mind. Like I said, general benefits of this approach is that you get really reliable tenant data isolation. Outages in a component of a tenant are generally very confined to one tenant. So if your backend goes down because of some random thing that's happening, it generally only affects that one customer, which is really nice. It completely decouples the infra teams from the product development teams, which is awesome. The CRD is a really nice, clean typed interface for everything that can be different about each tenant. So if something needs to be tweaked or modified, add it to the CRD. That creates a really nice interface for that. And all of this ecosystem is really fun and exciting. And if you do stuff like this, it'll be easy to find really smart people that want to work with you because they want to work on this technology too. Some pain points of this approach are you have to really maintain a strict culture of articulating your operations tasks in Go code. So if your SRE team is full of people that don't like writing Go and don't like, everything that you do for a tenant needs to be scaled across all of your tenants. So you need to incorporate all of these kind of individual tasks into some mechanism into Go software. So if your SRE team is really down to completely manage operations as a Go software development project, then this is awesome. If that's not what you're looking to do, don't do this for sure, because that's for sure what you're going to be doing. The other downside, I'd say the big downside of this is most people don't bend Kubernetes this way. They don't try to run a lot of really small tenants, or a lot of really small namespaces, rather. Kubernetes says that the limit of pods on a node is 110. If you try and pack as many pods as possible onto a tenant and you start approaching that number, things start to hang up and get really sketchy in really interesting ways. Also, once you scale past one cluster, custom resource definitions don't really work well at allowing you to articulate multi-cluster topics or ideas that span clusters. And obviously, observability is a constant challenge. And the fact that there's no server-side apply yet makes a lot of these kinds of operations somewhat unsafe. So there's a multi-tenancy working group that's doing really interesting stuff. That's led by David Oppenheimer, who was one of the people who wrote the Kubernetes research paper, which is awesome. So he's written a lot of great documents, as is Jesse, on the concepts of multi-tenancy that are super worth a read. There's also a new lead of that working group named Tasha, who I haven't met, but I'm looking forward to working with. There's a lot of great stuff going on in this working group, but they're mostly focused on establishing definitions, and working groups aren't long-lived and they don't produce code. So, based on what you like to contribute, that may or may not be something that you want to get involved with. And the other thing is Lesser, which is kind of a shell. I started working on a version of this that is open source, and it's basically just a shell of a controller for me to work on open source multi-tenancy concepts. So if you are interested in working on something like this, or you want something like this in your organization, and you want to work together on it, let me know, and maybe we can make something that's a little more generic for your use case. Now, I don't think I have time for questions, but that's all my contact information, and thank y'all for sticking with me.